The primary objective of vertical position control is highly specific. Establish the exact elevation of a point relative to a standardized datum. For generations, the baseline standard for achieving this has been optical differential leveling. This relies on a strict mechanical procedure. A surveyor establishes a perfectly horizontal plane of sight through an instrument like a dummy level, then reads the heights off graduated rods. By using short sights, back sights, and foresights, they march a known elevation step by step across a field. Because optical leveling demands numerous short-distance setups to maintain accuracy, the process becomes highly inefficient when engineers need to cross massive valleys or build interconnected national grids. Treating the Earth as a flat coordinate plane works flawlessly for a single building site. Scaling up requires abandoning simple geometry and confronting planetary physics. When surveyors need to establish major geodetic networks over vast distances, they transition to a method called trigonometric leveling. At these macro distances, transferring an elevation requires complex physical modeling rather than solving a simple right triangle. First, the spherical curvature of the Earth physically drops away from the instrument's horizontal line of sight. Second, changes in atmospheric density bend the incoming light itself. Finally, gravitational anomalies warp the very concept of what it means to be level. Achieving first-order precision at this scale relies entirely on mathematically neutralizing the Earth's physical interference. This diagram illustrates the direct method of trigonometric leveling. The surveyor measures the horizontal distance d and the zenith angle theta. These feed into a base equation. Target height, h, equals d times the tangent of theta plus the benchmark and instrument heights. The structural weakness of this specific equation is its strict assumption at a perfectly flat reference plane between the 2 points. In practice, this linear model functions reliably only if the distance to the target is less than roughly 300 meters. The moment a surveyor sights a target beyond that 300-meter threshold, the Earth's geometry begins to actively disrupt the calculation. Because the Earth is a spheroid, the ground physically pulls away downward from a perfectly straight, horizontal sightline. This schematic defines the curvature error variable, denoted as CC. It represents the growing gap between the mathematical horizontal line and the actual level line. This error increases exponentially, scaling with the square of the distance divided by twice the Earth's radius. In physical terms, a straight horizontal line gains approximately 0.0785 meters of false height for every square kilometer of distance. Left uncorrected over long distances, this curvature error systematically overcalculates elevations, rendering a geodetic network useless. We can correct the Earth's shape using pure geometry, but geometry cannot account for the physics of the light traveling through the air above it. The second major physical interference is that light does not travel in a perfectly straight line through the Earth's atmosphere. As shown, air density changes cause atmospheric refraction, bending the line of sight downward. This partial corrective to the curvature error is represented by CR. Surveyors use a combined correction formula for both phenomena, yielding the final adjustment variable, CCR. Mathematically, an adjustment of 0.067 times the square of the distance in kilometers is applied to the final height calculation. While this 0.067 factor is an industry standard, it relies on static assumptions about average air density. This exposes a massive vulnerability in the methodology. Refraction is the greatest source of error in leveling because it fluctuates wildly with changing temperatures and barometric pressure. Relying on a static mathematical estimate of 0.067 is entirely insufficient for high-precision control work on hot or shifting days. To bypass this, engineers utilize reciprocal leveling. In the field, a surveyor observes from point A to point B and immediately takes a reciprocal observation from B back to A, recording both angles. By averaging these sightlines, curvature and refraction errors mathematically cancel out. When the physics of the atmosphere make mathematical models unstable, surveyors must engineer their physical observation methods to bypass the atmosphere entirely. The ultimate test of vertical control lies in high-precision geodetic leveling networks that span entire continents. To verify these networks, engineers rely on a leveling loop. This is a continuous sequence of measurements that traverses hundreds of miles, but ultimately returns to the exact same starting benchmark. This creates a strict geometric paradox. If a surveyor uses flawless instruments, makes zero human errors, and perfectly cancels atmospheric refraction. Pure geometry dictates the final sum of the height differences must equal exactly 0. In reality, when summing up the height intervals on a massive loop, the total will almost never close to 0. This failure occurs because purely geometric leveling implicitly assumes the Earth's gravity field is perfectly regular and constant. To achieve first-order precision on a global scale, geometry alone is insufficient. The calculations must acknowledge the unequal distribution of mass inside the planet. Because the planet's internal density varies, true level surfaces do not form perfectly parallel planes. They form undulating equipotential gravity surfaces. Water always rests along these equipotential curves. This means 2 points can exist at the exact same geometric height, but water will still flow between them due to microscopic differences in gravity. The geopotential difference formula, shown here, provides the ultimate solution to the continental loop paradox. Under this model, surveyors multiply every single geometric height interval by the exact localized gravity reading measured at that specific location. Only then does the loop precisely zero out. This brings complex planetary scale physics directly back to the physical brass benchmarks embedded in the rock by surveyors in the field. A calculated vertical position cannot rely solely on a flat map's geometry. It demands an exact, mathematically rigorous measurement of the Earth's gravitational mass.